Hi student and audience, and this is the lecture 8. In lecture 7, we went through all the design of current loop and we evaluate the control to output transfer function with current loop closed, and we confirm the validity of our design. So next step is to design the voltage loop based on that information, and maybe the final step is to prove the everything, the validity, accuracy of your design, okay, the performance, stability of this converter, and the predictions will be compared with the measurement or simulation result. Then you can appreciate the accuracy and the simplicity of this design and analysis, primarily based on this asymptotic analysis. Okay. Forget about the sampling effect of the current mode control. You don't need that here. Okay. We went through this. So we complete this current loop design, and we are discussing this. We are about to discuss this voltage loop design equation. So basically, we will determine this, and this to have this structure. And we know the relationship between this integrated gain and this circuit component. And again, most of this circuit component is already determined. So you can determine this, and the CTR. We know CTR and the CJ. CJ is the capacitance between collector to emitter terminals of this phototransistor. We measured this CJ of this device itself is 1.3 nanofarad. Okay, if we need something more than this, so we'll determine this. If we need something more than this, we add something. Okay, if we need something smaller than this, you are in trouble. Okay, we cannot reduce this. Okay, maybe then we get rid of this IC, we use something else, okay? Or we sacrifice the performance of this converter, right? So I told you this is the lower limit is determined by this device of the coupler. There is the one bad aspect of this, using this IC and everything. If you are using discrete component, there is a lot of flexibility in your design. But many things are predetermined, then your freedom is limited. Okay. Fortunately, we need to have this value larger than the value provided this device. So we add something finally. Okay. Okay. So let's go through the procedure of determining this. This is a voltage loop. So this is the voltage loop design. Okay. Loop gain shaping. Okay. Loop gain is, I forgot to add some. This one is okay, right? Loop gain is, this is control to output transfer function with current loop closed. Then you multiply this voltage feedback compensation. That becomes loop gain. Okay. I think I should repeat this block diagram again somewhere there. Okay. Loop gain is, there is this voltage feedback compensation. Then you start from here and you go back and like this, and this internal loop and this. Okay, so loop gain is defined this with FVS here, right? So transfer function from here to there without FV, voltage feedback compensation, was GVCI. Okay, then obviously then loop gain is multiplication of this GVCI times FVS. Okay, so this is the expression we derived. So we have this constant gain and 2 0 and 2 pole, 2 0, but 1 0 is right half plane 0. So magnitude will be flat because order is same, but phase will be different because this is RHP 0. Okay, then we select this. We select it. This is 2-pole 1-0 compensation. This one is popularly used for the PWM converter with current mode control. This is almost constant. It's fixed. Okay. So this is the natural choice of this because most of the case this is the best structure. Right? This is a 2-pole 1-0 compensation. It's not a type 2 compensation. Type 2, type 3 is something else. Okay. In control theory, if you have 1 divided by S is type 1, 1 divided S squared is type 2, you remember that. Right? That is related with steady state error something. Okay, so don't use this stupid term here. 2-pole 1-0 circuit. And strategy of this is I went through this several times. Okay, so let me just repeat the conclusion. This omega PC is this one is located at this point because to cancel this one and this one, that provides some benefit. Okay, that will be clear later. So this is the first one, and if this one comes first, omega RHP is coming here, then place omega PC at this place. Okay, actually omega PC is placed minimum of omega ESR, omega RHP, and half the switching frequency. Okay. For our case, this one is the smallest, so this is located here. Okay. All right. And initially, we should have this integrator structure to achieve the DC regulation. Okay. So let's take it granted. Then this TM initially has -1 slope and the DC gain is infinity. It is declining with this slope from the 0 frequency. We cannot locate 0 here, okay, somewhere there, and it's coming down. Then at this frequency, we have this pole. So slope is changed from -1 to -2, and we have G, omega GC is placed before the omega CR, which is loop gain crossover frequency. Here, it's different from omega CI. This is appearing first here, this omega CR. Okay. Suppose this is absent, it's not existing. Then slope becomes -2 when it passes this 0 dB. Then phase margin becomes 0. Okay. System becomes unstable. To avoid that, to have the phase boost, you are placing this omega GC here, then phase will be increased. Okay, it is targeting to -180, but 0 is coming, that will go up. Okay, so phase will be increased. So here there is some reasonable or sufficient or acceptable phase margin will appear here, and it goes like this. And there is omega ESR, but you place the pole, it cancels. Then they cancels, they are not existing there. Then slope becomes -1, and at omega CI you have pole. Then slope becomes -2. Finally you have this. Then slope becomes -1. Okay. So purpose of canceling this is the ideal structure of this loop gain is this one, this integrator structure. From the low frequency to high frequency, that is the best one. Okay, but because of this structure, we cannot have that. Then we want to maximize the region frequency range of this -1 slope. Here, -1 slope is extended by just placing this compensation pole at the omega ESR. Okay, so that is the reason why you are placing that, and KB is desired loop gain crossover frequency omega CR. This is different from the omega CI. Omega CI is what is current loop crossover frequency. You should select some number between 10 to 30% of omega S. Okay, but this you want to place in the middle of this somewhere here, okay? You want to improve this, increase this, okay? Well, you cannot go like this. So there is a pole, and this is 0, but phase-wise, this is the pole. So somewhere here, okay? I'll tell you how to determine this later, but you should select this minus slope region somewhere here, okay? So KB is selected for the desired frequency of omega CR. Why is that? Take a look at this, okay? If we multiply this and this, then that becomes another constant. Then multiplication of this and this can be considered as the effective integrated gain. So if you extend this, then this frequency should be KVCI times KV, right? Initially, this minus one line segment is looking at this point, and in the middle it has this pole and 0, and pole and 0, something like that, right? So by changing this, by adjusting this, you can raise up or raise down, okay, without changing phase characteristic. Just you are relocating this omega CR frequency. Phase remain the same, okay? That provide a means of controlling phase margin as the final design trade-off, okay? You don't have to change it, just one number, then that phase margin will be moved around, okay? So we are using this. You know, this is the two-pole 1-0 structure using the optocoupler isolate feedback scheme, and the DC regulation is this one. So this VO is divided by these two resistance, okay? This current is very large compared to this, okay? Then this is the division of this. This is this one. So by changing this RX, you are adjusting this out voltage. So this is the 2.5 volt. To obtain 10 volt out voltage, it was 770 something like that. I don't know, maybe something like that. Okay, it is shown here. Okay, 720. Okay, all right. And this is the poles and zeros of this voltage feedback compensation as two-pole 1-0 compensation. And this parameter is determined like this. Rx is used to control the output voltage, and it does not appear in the expression of this compensation. And RB is something else to provide the sufficient bias for this OTA, operational transconductance amplifier, and this two-pole 1-0 compensation. And actually, this is the entire schematic of converter. So this scheme is very similar to the measurement of the loop gain, but this AC probe, AC something is connected here, right? Previously it was here. Then with that, we measure the control to out voltage with current closed, and if you connect here and here, then denominator is dot. Terminal is denominator. Is our voltage head numerator is connected this undotted terminal of this AC probe here. Okay, this is what? This is control voltage. Okay, so numerator is then FVS is no. Control to voltage feedback compensation. Input is voltage disturbance, and output is disturbance in control voltage. Okay, so this is the measurement set up to measure this voltage feedback compensation. Okay, And this two-pole 1-0 structure is obvious here. So with this integrator structure is here. And there is a 0 is coming first. And the pole is coming here. Okay? Okay, let me elaborate this. This structure is shown here. Something like this. This is omega G, omega PG. I used P. Okay? No, C. And this is the omega PC, right? And this phase is obvious. Okay, it comes from this minus 9 degree going up and going down, right? So this is very good, very convenient way of doing this, right? Because this the loading effect is negligible here because this OPM and here you have OPM. OPM has very large input impedance, so the loading effect can be ignored. Then you have very good approximation of this transfer function. Okay, so I repeated this. This is the same curve repeated here, right? Same thing. Now we revisit this lecture slide. So this explains the structuring or shaping the loop gain based on this control to output transfer function with current closed. The equation is this. Loop gain is just the product of this one, GVCI, which is this one. So we know the structure of this from the previous analysis. We evaluate the formation of this structure. And this is the two-pole 1-0 compensation we're going to use for this converter. So product of them is this one. Okay. Also we discussed the measuring this loop gain in the past, right? And the previous time we discussed how to measure this and this separately using the PSIM based on the time domain simulation computational method. Okay. And this is just the reference. So using this, we wrote down this, or we already know this equation, and this is the required the structure of voltage feedback compensation. So we start drawing from this asymptotic plot from the low frequency. Okay, so this is low frequency. So it starts with the integration, and integration gain is this one. This, no, not this one. This KV is integration gain. So it starts out with this integration, this times this divided by S is this one. So if you extend this slope without considering this poles and zeros, then this line segment is looking forward this point, and this point is KVCI times KV. Okay, this is the integration gain, but at this point, this is coming up. Okay, so we have this low frequency pole here. The slope is changed from -1 to -2, and we have 0 here. This omega GC, C means compensation, so 0 is here. Then this is the loop gain crossover frequency, omega CR. And at this point, it has in control to output transfer function, there is omega ESR, but we placed this compensation pole at this point, so they canceled. So it maintains this -1 slope of this point, and we have this pole, omega CI is current loop crossover frequency, and finally we are assuming this omega RHP, right plane 0 is coming last, but order can be changed This one will come first, something like that. Okay. So this is the structure. All right. So this is desired structure. The purpose of shaping in this manner is explained here. So this omega PC is used located to cancel omega ESR that extends the frequency range of -1 slope for the loop gain, and omega GC is placed before omega CR. If this is missing, then -2 slope will extend up to here. Then phase will be approaching -180 degree. Then the converter will be unstable. To avoid that, to have appropriate phase boost, you are placing omega GC before this loop gain crossover frequency. There is another consideration. Select the location of the omega GC, which is not apparent here, but I'll explain that in the next lecture slide. Okay, so omega PC is located at omega ESR to cancel the effect of this ESR 0, and we are assuming this frequency comes first, then this one, and we place the omega GC 0, compensation 0, before omega naught. Omega naught is power state double pole. It's not shown here. Okay, so you are not seeing this because this is cancelled. This is derived using the current loop in the denominator, and in the numerator there is a control to output transfer function times modulator gain, and that omega naught is cancelled. And actually the second order behavior is entire of second order characteristics are cancelled. So this is this single order minus, it has a single order -1 slope, but somewhere in between there was the omega naught. That is disappeared, okay, because of the internal current loop. That is the one purpose of employing the current loop, okay. So branch it was originally second order system, and with that feedback it becomes this single order system, which is much easier to compensate and to handle with, okay. All right. And this KB, so they are already determined, this one and this one, and the remaining undetermined parameter is KB. So KB directly controls this omega CR, loop gain crossover frequency. If you increase KB, the phase remains the same because this is just constant, and it will shift up this loop gain plot, shift up, okay. Then this omega CR will shift this direction to the higher frequencies. If you decrease this KB, and this will go down, and omega CR will shift it to the low frequency. Okay, so there is a direct relationship between this location of omega CR and this value. Okay, so KB will be determined by selecting this omega CR property. That is explained in this lecture slide. We already have this structure, and as I explained in the previous lecture slide, this initial line segment is looking at this point, and at this point, so up to this equation of this is this integrator gain divided by S. Okay? No. This gain divided by S. So if you evaluate the magnitude of loop gain at this point, that becomes, this is omega ID, okay? Then this magnitude is 20 log, this one, KVCI times KB, which is the gain, DC gain of your compensation, and divide by, we are evaluating, originally its denominator was S, but we are evaluating this magnitude at this particular frequency. So omega ID is coming in downstairs. Omega ID is here. So this is the value, asymptotic value at this point. Okay, so I wrote down here, And the design equation is, suppose you select this omega CR, loop gain crossover frequency at this point. This is your desired location of crossover frequency. Then assume this is fixed. Then you want to compute this value that actually place the loop gain crossover frequency at this point. Okay. Then there is a simple algebra. So this is the value. This is the starting value at this point, and this line is declining with -2 slope of this point. So declining minus and -2 slope, 40 dB per decade, and starting point is here, ending point is here, starting frequency, ending frequency. So you are here, okay? And from here to there, slope is -1, so -20 dB. Slope, so this is the equation. And this is the 1, so this is 0 dB, okay? So this is the equation in log scale, and you convert these things in linear scale. So here you have this, and this is, you have minus sign here, then you swap the numerator and the denominator, and for this, you scale this inside of this parenthesis, then you have this, and you solve this equation for kV. For given omega CR. So you select this, then this value will be determined. Okay? So now every value, 3 unknowns are determined. So design is fixed. Okay? So selection of these corner frequencies and the crossover frequency are summarized here. Okay? I already explained this, okay, but this is the summary, all right? So, compensation pole, which is this, we place this compensation pole at the minimum of 3 frequencies. First one is RHP0, and second one is ESR0, and this one is the Hafter switching frequency, okay? Which one will come first? Whichever comes first, then select omega PC at that frequency, and the compensation 0 is placed this, okay? So this should be placed before the loop gain crossover frequency, but before loop gain crossover frequency, the omega not double pole frequency is coming before that. So actually the order of 3 frequencies are omega GC is coming first, and this is a double pole frequency. It's not showing here, okay, but we know this. Later on, we will calculate this, okay, and these 2 of them are below the loop gain crossover frequency, okay. So obviously, omega GC is below the double pole frequency, omega naught. Omega GC, okay. I'll explain why we are using this strategy, okay. Later on, you will see this omega GC determines the time constant of transient response in time domain, okay. So step load change response, step input change response, and all other transient response, speed of transient response, time constant of that is determined at this frequency. So to have faster response, this omega GC should appear at higher frequency. Okay? But there is another problem. That problem is not apparent here. But some other analysis, some detailed analysis show that if omega GC exceeds this omega naught, the system becomes, converter becomes conditionally stable system, which is very bad. Okay, actually the worse than unstable system. So to avoid that situation, this is the strategy we are taking. Okay, and this is obvious. Okay, and to have the phase boost in advance, this should come earlier than these 2 frequencies. Okay, so that is not shown here. But this situation is very similar to the case of voltage mode control. And there is another class of analysis, two-loop system analysis. If you use that, you clearly see this requirement, but it's not shown here because we already include the current loop is embedded in GVC expression, and that was cancelled because of this numerator and denominator. There are common factors because that is not shown here, but this should be observed. Okay, so this is requirement, and select the TM loop gain crossover frequency before omega RHP. This is a right hand plane 0, so it introduces 90-degree phase delay. So it hurts the phase of your loop gain. So you should avoid this one by placing this loop gain crossover frequency well below this frequency. Okay. Otherwise, this minus 90 phase delay will destabilize your converter. So to avoid that situation, this comes earlier, well below this frequency. So good number is 10%, from 10% to 30% of this number. This is the very good practice. Okay. So this is my recommendation. This is my recommendation. Then you will have good design in general, except for the special case. 99% the design will be very good. And finally, so this is determined, and to determine this, you already selected this, then you select this, you decide this, then this is naturally coming out with this simple algebraic equation, just division, multiplication will give this number. Okay, with this, maybe you simulate the loop gain. Okay, so make sure the phase is somewhere here between the 45 degree and the 70 degree, maybe 60 degree is a good number. Okay, this one is a good number. If you go further this direction, the phase margin is very good, but with that you are sacrificing. You should sacrifice something else. Okay, so if you go this direction, the other performance will be good, but you are in the danger of being unstable. Stability margin is so small. Okay. Oh, not this one, this number. Okay. So there is a between phase margin and other performance design trade-off is in between. All right. So this one, not this one. This one. I was talking about this. Okay. And finally, because every the parameter number, the values of parameter component are determined, then you compute the value of circuit component based on the equation. We already derived that, or I showed many times. So this is the example of our prototype converter, and the operating point was this one. This is not the best choice. Okay, but because I select this point, so I was very conservative in selecting everything at that time. Then justify selecting this not unsuitable operating point. Okay, I forgot that, and I finished up everything. So I don't want to go back and to fix everything. So I'm still keeping this. All right. So duty ratio is this one, and this is a control to output transfer function, and KVD, this is the double pole frequency omega naught, and RHP, right hand plane 0, and this comes from the control to duty ratio to inductor current transfer function. This is the duty ratio to output transfer function. Okay, we already went through this, and this is the 0 frequency there, and ESR 0 is here. Okay, so with this background, we select the exact location of compensation pole 0 and integrator gain. So comparing these three numbers on this page, and this switching frequency was 70 kilohertz, something like that. So this is the minimum. So we select this as the location of this compensation pole, and this compensation 0, it was 0.6 to 0.8. So I select some strange number, 0.76. Okay, so my suggestion was some number, any number between these two boundaries. So this is okay. And the TM, loop gain crossover frequency, omega CR, was, the suggestion was, recommendation was 0.1 to 0.3. So 0.16 is rather conservative design. Okay, so we will have the good phase margin and integrated gain. You select this is calculated, then using this value and these values, kV, gain of your voltage feedback compensation, low frequency gain is selected as this. Okay. Obviously, the next step is to determine the circuit component values and the location of various corner frequencies is explained here. So omega GC is coming first, and omega naught is double pole frequency of power stage. Omega ESR is coming later. We placed omega GP, omega PC. Omega PC is located here, so they are cancelled. And later on, loop gain crossover frequency is here. And we have another pole, omega CI. No. This is the loop gain crossover frequency, and this is the crossover frequency of the current loop. And finally, the right half plane is coming next. Okay, so this is the order of our corner frequencies, but you are not seeing this in the simulation result. They are very close. Okay, it is not easy to distinguish these frequencies. Okay, they are merged together. So with this, and this is the compensation structure, we're going to use voltage feedback compensation. So we should determine these values 1, 2, 3, 4. Okay, this is something else. This is to provide sufficient bias current for this OTA, and this is to determine the output voltage, DC regulation point. So there are 4 variables to be determined. Okay, and this is the equation of this voltage feedback compensation and relationship between this. As I said, Rx is just controlling the out voltage value, and RB is required to bias current for this OTA, and the compensation parameter is only influenced by this RB. Okay, so this is nothing. All right. We know the expression of the kV and the desired value of kV, and we know the expression of this one, omega PC, and the desired value, and omega GC, and the required value. Okay, and these values are determined by the IC designer. So RT, R1, R2, CTR as given, we measured somehow, or we obtained from the data. The vendor provided data is used to determine this CTR, and we experimentally measured this optocoupler capacitor. CJ prime is 1.3 nanofarad. Okay, so then we should determine the remaining 1, 2, 3, 4, but we only have 3 equations. So unknowns are 4. but we have three equation. Then you select one arbitrarily, not arbitrarily, some reasonable number. So maybe 2.2K is okay. This is the standard resistor. Don't select something very small, very large. So maybe the 10 kilo ohm is okay, or 2.2. This is the standard resistor, so I selected this. Then you select RX, this one, to regulate our voltage at 10. Okay, there is a simple relationship using the virtual short feature of these two terminals. Okay, and with this, and this are selected, and from this, and you have chosen this in advance, then remaining values are determined, and the calculate value of CJ was 2.3 nanofarad, but this the parasitic capacitance of this optocoupler is this 1.3 nanofarad, and you add one nanofarad capacitor in parallel to this to make this number. Okay, so this is okay, right? If it requires the value smaller than this, then you are in trouble. You should modify something, okay? But this time it was okay. So external capacitor of 1 nanofarad is added in parallel with the parasitic capacitance of this optocoupler device. And finally, this RB is determined, okay? And you can confirm this. The out voltage is 10 volt, and this is 470 ohm, okay? This is 470 ohm. This is 1 volt approximately. Then this IX is much larger than 1 milliamp, and this VX is sufficiently larger than 2.5. Okay, so because of this, I select this. All right, so everything is selected. Then next step will be the evaluation of the performance, frequency domain performance, and the time domain performance of this converter, experimental converter, and the loop gain measurement. So this diagram is the same or very similar to the previous ones used for the evaluation of control to output transfer function with current knob closed, or the transfer function of this optocoupler isolated voltage feedback circuit. Okay, because this is a disturbance, so disturbance is already there. Just moving around this AC probe, you can measure different things. This is the place to measure the loop gain. So as I said, this notation, so dot is here, then denominator is Vx, assume this is Vx, and numerator is this one, VO here. So what you are getting is this is a loop gain. Okay, so just placing this AC probe in this manner, you are getting this loop gain magnitude. Okay, so this is the loop gain magnitude. Okay, and the phase is this the AC probe is just showing the phase of Vx, phase of Vx minus phase of our voltage. Okay, so for this case, this one is 0. This is we are assuming this is the reference, so can be considered 0. So what you are seeing is here is minus this one. Okay, that is the loop gain phase here. Okay, so you are using this minus sign to cancel. Actually, this is good. It cancels the negative feature, negative feedback feature of this scheme, this loop gain, right? So if phase is this minus 180 degree, and you consider the negative feedback, all right, then phase becomes 360 degree negative. There is just one complete circulation of this, okay? That means if you add the signal here, then that signal is coming out exactly the same phase. Then this returning sinusoidal waveform, it has larger magnitude than this injected sinusoidal wave. Then system is what? Unstable. Okay? If there is smaller than unity, system is stable. If there is the just unity, then this magnitude of this is the same. There is the oscillation. It generates the sustained oscillation. There is not a converter. There is also unaccelerable. Okay? So this is this AC proof is well designed in this purpose. Okay? You understand this, right? So that is why you are seeing this negative number here. So why you are concerning about the frequency, the magnitude of a frequency at this magnitude at the frequency where the phase of this signal falls to minus 180 degree. Okay, because there is additional 180 degree phase delay in the system. The two of them combined, it generates the same input, the output sinusoid, exactly same phase with the input injection signal, and then you are just comparing the magnitude curve. You can judge the stability of the system. Okay, that is the basic fundamentals about phase margin, gain margin, and the stability evaluation of using the Bode plot of the loop gain. Okay, that is the essential summary about this everything. Okay, so many students and many engineers, they just blindly watch this, and they are saying the phase margin is some number and the converter is stable. But the story, theoretical story behind that practice is what I said already to you there. Okay. So keep that in mind. So this is the phase margin is about 60 degree, which is very good. Okay, and the phase is declining here rather rapidly. It decays. The slope should be minus 90 degree per decade. Okay, because at high frequency we have one pole. Omega Ci is here, was here, should be there. Okay, let me use this purple color. This is a pole, omega Ci, plus we have omega RHP, which is 0, located at phase. Okay, so this will introduce 90 degree phase delay, and this will introduce another 90 degree phase delay. And the slope of this phase delay is minus 45 degree per decade. Okay, this is not a double pole. If there is a double pole, phase will drop immediately by 180 degree. But this is the two single poles. Okay, so slope is minus 45 degree plus minus 45 degree, another minus 45 degree. Then this decaying slope should be minus 90 degree per decade. Okay, so slope is very similar to that. Okay, but at this high frequency region, the accuracy of this small signal model becomes very poor. Okay, so there is just something else, and the accuracy is not guaranteed. So you have some error here, but this makes sense because of with this there is almost 90 degree phase delay for 1 decade. Okay, so approaching to this is very dangerous. So you should stay inside of this. So this 60 degree phase margin is very good number for the flyback converter. This is very easy to achieve for the buck converter, but for the flyback converter, there is a RHP 0. Okay, so it's not easy to obtain this. So everything is optimally designed at the given operating point, which is not ideally selected, but still this is a good design because of this very conservative design. Okay, and output impedance measurement. This is not measurement, simulation. Okay, of course you can use the small signal model, linear time invariant circuit model to evaluate everything. Okay, then you will have a clean curve, but this is better. Okay, this is almost the same as the experimental measurement done using computer. So this is good. Okay, so in the design steps, we use the analytical result, transfer functions and everything. Okay, in the past, people they simulate everything using small signal model, which is very cumbersome, and this is very simple, but you should know what you are doing and the implication of the result of your simulation. Okay, that is very important. With that, I recommend you use this method. Then you can save time, a lot of time. Okay, and this is another setup to output impedance of this converter. So this is the AC proof. It has the similar function here, and this is 1 ohm. Okay, 1 ohm. So voltage across this denote this as Vx. This is 1 times I naught. I naught is disturbance in output current. Okay, so what we are measuring is actually voltage, but that can be considered as a current. Okay, so with this, you don't need to use any current proof, so voltage proof is okay. So this is one good practice. Okay, you can save the current proof, which is expensive and which is not accurate sometimes. Okay, the voltage proof is much more accurate than current proof. So but you should use very precision resistance here to get 1 ohm. Okay, so I don't go through the details about this, but you can similarly understand why this setup measures the output impedance, and this is the output impedance measured. Simulate. Okay, if you measure these things with the hardware, you can use the same setup for the hardware, then you will measure something very similar to this. Okay, and it shows something here. So maybe this can be considered the pole here. This. Okay, the slope is changing by 1. Okay, slope is decreased by 1. That means there is a pole, and this pole, location of this pole is actually compensation 0. This was 0 in compensation, but compensation 0. During this process, it comes in the denominator because 1 plus Tm is everything. The output impedance is determined 1 plus Tm. You kick out 1, then Tm is denominator. So 0 becomes pole becomes 0. Okay, that is their load is swapped. Okay, so this compensation 0 works as the pole here, and this pole determines the speed. Okay, and there is this double pole feature here. So this can be considered the second order characteristics, and this frequency is somewhere, not exactly, but somewhere around CR. CR. I was using capital R or lowercase r. Okay, CR. Okay, this is location of the loop gain or loop gain crossover frequency, and this is the second order because you are seeing some peaking. Okay, but peaking is not big, so there is a minor peaking, and the phase is dropping gradually. If there is a sharp peaking, phase dropping was observed, all right? So there is a slow, weak, gradual phase decay. Okay? If you have this is a second order feature, then what will you have in your time domain response? This second order is generating oscillatory behavior. So from this, there are a lot of information. This is related with compensation zero, and this is the loop gain crossover frequency, and the magnitude of peaking is related with the oscillatory behavior of time domain response, right? So this is step load response. Step load response is this one. VOT is step load response in time domain. Okay. Then this one is GOS, output impedance is current disturbance to output voltage transfer function, and the step input is, you use this, I step is size of step change, okay. Then this is the S domain expression of VOS, okay, but we want VOT, time domain expression. Then you take this whole and take inverse Laplace transformation. Let me use this notation. -1 is inverse Laplace transformation. Let me repeat this. This is the load current to output transfer function. This is a disturbance source. So S domain expression of step load change, step change in load current, and this is the S domain expression of this output voltage. But you take inverse Laplace transformation to predict the time domain waveform of output voltage. Okay. So with that, maybe you can plot this one. You can predict the envelope of this waveform very closely. If you use some software, you predict this, okay? And multiply that, and you take this and plot this, then you will have this, except the ripple component, okay? All right. If you take a look at this, there are two different behavior here. There is some oscillatory behavior, something similar to this. Okay, it appears here and disappears soon, very soon, because this is fast, and there is some first order exponential decay here. Time constant of this is 1 divided by omega gc, because the pole is coming here. So this determines this time constant of this exponential type decaying waveforms. And this first small oscillatory behavior is coming from this part, and the frequency of that oscillation, decaying oscillation or temporarily transiting oscillation, is estimated from this frequency. They should be the same frequency. Okay, so this is the way of relating or predicting the time domain transient response from the frequency domain transfer function, Bode plot, output impedance, something like that. Okay, right. If you just watch this without thinking blindly, then this is meaningless. But if you have some idea, some fundamental idea, you can extract all our information about the system. Okay, and this is output impedance, and I'm comparing this in parallel. So this one is governing this part, and this one is governing this part. I already explained that here. Okay, so same thing. And the experimental measurement. So this one is very similar to this. This is the PCM, time domain simulation. This is the different from the computational method. This is the purely time domain simulation, and this was experimental measurement. They're almost the same. Okay, so everything is accurate. Okay. Similar analysis. This is audio susceptibility analysis. So this is the simulation result using this. Okay. So this is the input disturbance is coming in here. This is the input, and you just measure this. There is the input to output transfer function. Okay. You don't need the two terminal AC probe. So this is the reference, and you just measure this. Then you provide transfer function from here to there. Okay. Previously, the inject point and the measuring point, input point of measurement was different. So we used two-port AC probe, but here you can use just one single AC probe. And again, this is pole here. Then this is the omega GC, and the same thing. This is the loop gain, crossover frequency, omega CR, right? And the phase delay is gradual, more gradual than previous. So this oscillatory behavior was weak here, but in this case, oscillatory behavior is weaker than previous case, because the second order behavior of this one is very weaker than previous case. Okay, let me show you the step impulse response. So step impulse response has the similar behavior here. Okay, so let me show this. The same thing. Okay, so I compared this audio susceptibility and the step impulse response in parallel. Okay, the step impulse response, transient response out voltage in response to step change in the input voltage is same as the previous case. Here you have this AUS, this is the audio susceptibility transfer function, and this is the V step divided by S. This is the S domain expression of unit step times this is a magnitude of step. Okay, so we have pole, this pole, GC. It is a pole, but it was 0 in compensation. So this omega GC is determining behavior here, and this double pole occurs at the loop gain crossover frequency is, I don't know, somewhere here. Okay, they are different. The pattern is different. Okay, but this the second order behavior, oscillatory behavior, is much weaker than previous case because this peak is very small. Okay, maybe almost no peak here. Okay, and this is another story. I didn't discuss the DCM operation in this class, but I lectured many times about DCM operation. So the all converter should go in DCM operation in practical case. Okay, if the converter goes in the DCM operation, the converter power stage becomes very similar to the first order system. Okay, so everything will change. But when you are designing this compensation, you take the case of CCM. CCM is worst case because CCM we have second order dynamics. So second order dynamics is worse than first order dynamics because of the phase drop at the double pole. Okay, so you design everything in assuming the CCM and the converter is go to in the DCM operation. then what will happen is it is shown here. So this is the CCM characteristic, okay, of loop gain, and this is the DCM characteristic of loop gain. They are very similar, okay, they are different, but the shape and everything remain the same, only slight change in this direction, okay, and the borderline between CCM and DCM operation is determined by value of the R, load resistance, and the value at the borderline between CCM, DCM is denoted as R critical, and this is determined by converter topology. For the flyback converter, that is this one, and this value is 3.3 ohm. So this is the CCM and this is the DCM. If R is further increase, load current is further decreasing, that it goes deeper into the DCM. They remain the same, almost remain the same. This is the case of the current mode control. But if you use the CCM, that case is entirely different. Okay, for the CCM, voltage mode control. Okay, this is the case of the current mode control. Okay, for the voltage mode control, loop gain will be something very different here. Something like this. Okay, so there are a huge change in the shape of the loop gain. This is the CCM, and DCM will be similar to this. DCM maybe remain the same, but CCM case will be very different. Then all the dynamics are different. Okay, if you suppose you employ the current voltage mode control, not current mode control, then performance your converter in CCM is acceptable. But if you go into DCM, the overshoot will be increased, undershoot will be increased, and this response time becomes way slower than previous case. There is a huge deviation in terms of the converter performance in CCM and the DCM, which is very bad. Okay, so another advantage of this current mode control is the sensitivity of converter performance, depending on its operational mode, is much reduced. All right? Okay, so if you need more information, go to the YouTube channel or OCW site. So everything is discussed here. And this, I posted some additional lecture slide. Okay, let me discuss that. So there are many additional lecture slides that is related with PSIM simulation or interpretation of the simulation result, relating the frequency domain response to the time domain performance. That is very useful and very informative. But I skipped that. So I want to finish up this flyback converter business today. Okay, so I skipped many things, but I decided to keep this one. Okay, so this is the two-pole 1-0 circuit we employed in our prototype converter. So again, this is the expression of this compensation parameter in terms of its circuit component, and omega PC is determined by this. So CJ can be varied depending on the temperature or something else, so very sensitive to the operational environment. For that case, this is the exaggerated explanation, somewhat exaggerated, okay, but not entirely exaggerated. Okay, I made one mistake here. So in here you have pole, actually pole is here. This is the omega Ci, this current loop crossover frequency. We have pole, then this slope becomes slope. This is loop gain, -1, -2, -1 here. Forget about this, okay? I'll explain this later. Minus 1 is like this, and with this, it becomes minus 2, okay? Because of the additional pole, and we have this right half plane 0. 0 is 0 in terms of magnitude. The final slope is still minus 1. Minus 1 slope. Okay, not this 0 slope. This was wrong. But at this high frequency, this prediction can be erroneous. It takes some error. Okay, but this is a theoretical prediction anyway. Okay. And this pole, omega PC expression is Cj RT parallel with R1 plus R2. All of these three resistance are determined by the IC guy. Okay. So with this, think about what will happen if Cj is increasing. Okay. Cj is increased. So in this direction is larger Cj or not smaller. This omega PC at lower frequency. Okay? You understand this? Okay? If you increase this will be reduced. Then this omega PC, originally omega PC was here. So this is original design. And somehow you increase the Cj or some reason, some unknown reasons, then this will be this one. So this will be increased. Then loop gain crossover frequency is this one, and originally it was this one. And if you further increase this Cj, then loop gain crossover frequency will be here. Okay, will be here, right? So let me extend this, and this is. So think about the phase. Phase is initially here is it was not easy to draw this. Phase was because you have -1 and -2, so phase is something similar to this, and it stays -1 slope, so maybe 90 degree something, and it goes down like this. Okay, here we have slope here and rapid slope. Okay, this is pole actually when phase is concerned. So this is original. No. Okay, this is a phase. Okay, original phase. Then suppose this is -180 degree line, and then -90 degree was somewhere here. -90 degree here. Okay, the original design phase margin is this much. Okay, you increase this Cj value somewhat. Okay, this one. Then phase margin will be this one, not this one, because this pole is shifted to a lower frequency. Okay, so damage of pole is coming earlier. So for second case, this one will be something like this. Another one will be something like this. Okay, then phase margin will be this one, and the phase margin will be this one. Okay, because there is a change in the loop gain crossover frequency is shifting toward the lower frequency, and because of this pole is coming earlier, phase boosting is gone and the phase is decaying faster. All right, so this is the case. So I simulate this. This is some extreme case. This won't happen in practice, but I like to show this. Okay, So I showed this long time ago to the engineers to understand the significance of very small things on the performance of the converter. Okay, so the CJ was varied from here and maybe 10 times. Okay, then first was this one. This red curve is, oh, I don't see clearly, getting old. Then phase margin is this one. First case, phase margin is this much. Okay. Second case, the loop gain crossover frequency is here, and the phase is this blue one. Then phase margin is this much, and this green curve, loop gain crossover frequency is here, and phase margin is here, and the phase margin, next one is this phase margin is vanishing. Okay, so this is the case. This is 2.3. This is 26.3. This is 8.3. Something like this. Okay, so this is the original design, and this is the CJ is increased. I don't know. Okay, for some reason, but it shows something very significant. Okay, then loop gain crossover frequency is declining, and the phase margin is vanishing. Then what will happen? The output impedance. So output impedance, the peak occurs at the crossover frequency. Okay, so this peaking always occurs in the frequency neighborhood of loop gain crossover frequency. So this. Okay, and small phase margin increase the peaking. All right. So smaller, this is a larger CJ, and also it generates smaller PM, and output impedance becomes ugly, more ugly here. This is the worst case among these five. Okay, then this will affect the step load transient response. Which manner? If you move this direction, you increase the CJ in this manner, then this large peaking indicate what? Oscillatory. Okay? And this low frequency peaking means what? Low frequency oscillation. Okay? So the oscillation will occur, and the frequency of oscillation becomes larger, smaller period becomes larger. So sluggish is very similar to the slow. Okay, sluggish and more oscillatory. Okay, so that is our prediction, and I did the simulation here. This is the startup. Okay, forget about this. Okay, this is a startup. There is no soft start in my simulation, and this is the step load response. So the initial design, this disturbance, this is very small. Okay, and this is the CJ of 2.3 nanofarad. And this is 8.3 nanofarad, and increased. Then finally you have this one. Okay, so this one is our voltage, another one is current. I don't know which one is which. Okay, that one is our voltage. So our voltage becomes oscillatory, more oscillatory, and becomes more slow. Okay, finally. This is almost unstable. This is unstable. This is unstable. Okay, very small phase margin is almost unstable. the oscillation is not growing, but this is not a power supply. Okay? So this one single component affect the performance of this converter profoundly, right? Similar situation will occur. You have, okay, this is the end of this lecture. It's something else. You have power supply, okay? Then you bought somewhere. Then you may add capacitor in parallel with your output capacitor to improve something, okay? That disturb the location of the ESR, okay? If you add one large capacitor has a small ESR, then parallel combination of previous one and this one becomes way smaller than this. Then that ESR 0 is moved to higher frequency, but compensation pole is still locating at low frequency. Then pole becomes what? Bomb. Okay? Then the converter becomes unstable. Right? Many students or many engineers, if they have power supply, okay, they arbitrarily add output capacitor to reduce the ripple component, then it can make the converter unstable. I saw that case so many times. Okay. Another case is there is a capacitor, electric capacitor, which has large ESR. So you buy very expensive, some fancy capacitor, expensive one, and small ESR. It causes the same problem. Okay. Then you should change the controller appropriately. Otherwise, you are making your converter unstable. Okay. Same is true. If many people, they arbitrarily connect the capacitor in the input port of their converter, okay, that can cause a problem, potential problem. Right? So everything should be done with some engineering inside. Okay? Otherwise, you will experience some surprise in many times. Right? Okay. All right, this is end of this flyback converter business.